Before we move forward to our main topic of this lecture, I want to discuss two statements which may confuse you. When we were discussing about the similarities between the insulator and semiconductor, I said that at 0 Kelvin, all the electrons in the semiconductor are in the valence band. And in the last lecture only, we said that Fermi energy level is the energy level at which the probability of finding an electron is 1 by 2 at all the temperatures, and also at 0 Kelvin all the energy states below Fermi energy level are occupied by electrons. The statement of Fermi energy level is actually true. The thing is, when we were talking about the similarities and differences between insulator and semiconductor, I did not taught you about Fermi energy level. So at that time, this point was not introduced. But after studying the Fermi energy level, it should be clear to you that not only the states which are below the valence band, but all the states which are below the Fermi energy level are occupied at 0 Kelvin, even though there will be some energy states which are above the valence band. Now, we will talk about extrinsic semiconductor and will talk about the parameters on which its Fermi level is dependent. Not only the Fermi level changes with temperature, but it also depends upon the doping concentration. Here we have taken an n-type semiconductor for the purpose of our analysis, and somewhat similar results will be obtained in the p-type semiconductor as well. For simplicity, we will now fix the doping concentration and vary temperature only. This red line is representing the intrinsic Fermi energy level. This is representing the donor energy level. This is conduction band energy, and this is valence band energy. This blue line is representing Fermi energy level of extrinsic semiconductor. At T is equal to 0 Kelvin, you can see that Fermi energy level lies halfway between conduction band and donor energy level. Whereas as the temperature is increased, it falls down, and at very high temperature it finally comes very close to intrinsic semiconductor Fermi energy level. This temperature is usually greater than 600, but there is no need to remember this value because it also depends upon the doping concentration. So you should remember that at high temperature, the Fermi level of extrinsic semiconductor comes closer to intrinsic Fermi energy level. It also means that at very high temperature, the extrinsic semiconductor behaves like an intrinsic semiconductor, and at room temperature, the Fermi energy level of the n-type semiconductor lie below the donor energy level. Similarly, we can observe the change in Fermi energy level with temperature in p-type semiconductor. Here also, at T is equal to 0 Kelvin, EF lies in the middle of acceptor energy level EA and valence band energy level EV. And at room temperature, EF lies above acceptor energy level EA, and at high temperature, EF approaches intrinsic Fermi energy level. Therefore, extrinsic semiconductor at high temperature behaves more like an intrinsic semiconductor. And obviously, here also we have assumed that the doping concentration of acceptor atoms is constant. It should be clear to you by now that the Fermi energy level of extrinsic semiconductor depends not only on temperature but doping concentration as well. Only for simplicity, we have assumed the doping concentration to be constant so that we can analyze the change in Fermi energy level with respect to temperature.